everybody. You may be watching this video for a variety of reasons. One of them may be because you are in a virtual setting. Another may be that we kind of ran over class time. And then another may be that you weren't here for the notes. But these notes are the mini big picture notes for the lab that you did where you just dropped the ball once, let it bounce once, and then you collected about 12 points of position versus time data. And what we really looked at while we did this very mini lab was gravity, which has a really big conclusion for something that data collection wise was very simple. So what we're going to be looking at in this kind of brief video is how does gravity affect motion on Earth? And we're just going to kind of scratch the surface with this because right now we're just looking at how is it affected, not why it does that. So taking a look just like normal at what we saw. So I did take some of the results that were posted into class, and we saw that when we looked at position versus time data, you got this really nice quadratic formula or parabolic relationship. Either way, you saw pretty much that the object went from fast to slow, going away. Then it had kind of a peak point, and then it went slow to fast back towards the reference point, all in one steady motion. Then you went through doing all of the slope formula, the 11 or so times, because you plotted what was the average velocity versus the midpoint time in order to get this velocity versus time graph. So what you actually saw was just that one continuous linear line that started in the positive component and then went to the negative, which qualitatively makes sense. Again, you started from fast and then went slow going away. Then you reach that kind of maximum point. And something kind of important happens there. And then you're now going into the negative component because you're going towards the reference point from slow to fast, so your values are getting bigger, just in the negative. And since this is a really nice linear trend, what we actually find is that you have one single uniform acceleration regardless of the fact that you're going up and coming back down. And that fact really is due to gravity, because gravity is the thing that's acting on it as it goes up and as it goes down. It's the reason why it slows down on the way up and the reason why it gets faster as it comes down. So we get this one singular acceleration. And when you looked at kind of everybody's, whether you looked at everybody in the virtual format or whether you looked at it in class, we found that the values were hovering in between 9 and 10. Even if we look at this mathematical model that was created here, this number truly is 1/2 times A. So that's why we're seeing half of that, either 9.4, I think that's like 9.7, but it's half of our overall acceleration because it's being multiplied by the 1/2, because the 1/2 AT squared plus VIT plus XI. So if you can compare that value to the one that you get for your velocity model, whatever you get for your acceleration, again, you're all kind of hovering around this like -9, -10. Which leads us to some very key and very big conclusions. And those conclusions, like I said, are all revolving around gravity. So the biggest conclusion that we can make from all of this is that yes, we are dealing with a uniform acceleration regardless of the direction that the object is going, regardless of the fact that it hit, it bounced up, came back down, you still get one single acceleration. And that is because gravity pulls us downward at one singular uniform rate. And that singular uniform rate is -9.8 meters per second squared when in free fall, and this is regardless of an object's mass. And after you complete this video, you should watch the BBC video that actually proves that gravity doesn't care about what mass you have, it doesn't care about the shape, size, or otherwise, it's going to pull everything down the exact same way. So when I say that we have the -9.8 in free fall, that's kind of a very specific thing. Free fall is an absence of all external forces other than gravity, meaning gravity is the only thing affecting this right now. So even though you drop the ball, as soon as you drop it, you're not touching it anymore. You are not putting an external force on that object after you release it. And even the floor, as soon as it leaves the floor, even though it's springing upwards, nothing is touching the ball except for gravity. So even if something is kicked, thrown, shot, it doesn't matter. Just like the soccer ball on this right-hand side, as soon as the foot or the object is no longer touching the ball, the object is in free fall, and gravity takes over. So gravity pulls, and that is one of the misconceptions in physics. People will kind of incorrectly say, oh, gravity's pushing me down. It does not. Gravity is a pulling force. So it's trying to pull you towards the center of the earth. And that's something that we'll kind of talk about a little bit later when we talk about circular motion is why is it trying to pull us to the center? And again, this is regardless of the object's direction. So when the ball was bouncing upwards, gravity was still acting on it. So yes, it had some velocity as it was going up, but we saw that gravity was trying to pull it down, right? And that's why it was slowing and slowing and slowing until it hit its peak. And then it said, okay, gravity, you win. And it started to come back down. And then that's when gravity was working in the ball's favor. So that's why it got faster as it came down. And then I have here that this is why it's a constant value of that negative 9.8, because like I said, you're slowing on the way up, which gives us that negative, but then you're speeding up on the way down, which down is going to be towards, so again, giving you that overall negative 9.8. Now, one of the points that I kind of mentioned when we were looking back here is that the maximum height matters. Because what happens at the maximum height? Well, the ball goes up, and then all of a sudden the ball says, okay, gravity, you won, now I'm going to change direction. Well, in order to change direction, your velocity goes to 0. It's very momentary, but it does. And that's what we see when we get to this intersection here. We actually see that trend line go through 0, and it should. And that 0 means that you are at the maximum height, and now you're turning around. So that is a huge conclusion, that the final velocity at maximum height is 0. And I will say that over and over and over and over again because it is so important. And you will use it all the time. You will use this even in AP Physics too because it is such an important point. Especially when we move on to Unit 4, which is projectile motion, we're going to be dealing with maximum heights all the time because that's our turnaround spot. So this is huge, and this is something that you need to know right now. So highlight it, put a star, do something to remind yourself that maximum height equals a velocity of 0. But do remember that acceleration is still negative 9.8 because although you're 0 in that moment, acceleration is still a change in velocity. So y2 minus y1 over x2 minus x1 for your velocity graph. So 0 isn't y2 and y1, it's only a singular point. So acceleration is still negative 9.8. Gravity doesn't care that you're at the peak. It's still going to pull you downwards at the same rate. And that is a very typical AP question right there. Oh, whoa, look at that. I have a slide there that shouldn't be. There we go. All right, so example 1. So right now at this point, you should have the 3 example problems pulled up. This one looked at a pretty rude squirrel. So what I expect to see is automatically that given versus known chart. We know that the object is going to start at 12.5 meters. It's going to end on the poor kid's head. So that's going to be the 1.6 meters. Initial velocity, you are just holding the object, so nothing's happening. So that's going to be 0. As far as the final velocity, I didn't ask you for it, I didn't give it to you, so I don't really care about it. Now, the nice thing about a gravity problem or a free fall problem is that you can automatically put in that acceleration is negative 9.8. And then we're trying to solve for the time. So we plug everything in and we get that the time is 1.49 seconds. And feel free to pause this video so that you could get this in your notebook because I do expect the examples in your notebook. Anything that I put on a board, in a video, in a Google Meet should be in your notebook so that you can look back at these notes. Question number 2, looked at that poor worm that was dropped. Once again, you were given the initial position of 185 meters. It lands on the ground. The initial velocity is going to be 0 because it's initially just being held there and then dropped. And for this problem, you want to know what the final velocity is. We know that acceleration is going to be negative 9.8, and we don't know the time, but we know that we definitely need the time in order to solve for that final velocity. So starting with our delta x equation first, we can solve for t and then plug back into our VF equation. Now, if we look at the answer that we get for the VF, we get a negative. And that's a good thing. For whatever reason, people always get very leery of the fact that they got a negative value and they think that they're somehow wrong, and you're not. Because think about it, the worm is traveling back towards the ground. They're traveling towards the reference point. So your towards velocity should be negative. So all of that makes sense. Now, example number 3 is the one that we need to pay a little bit more attention to. So this is a pretty common problem. So you were asked to solve for what is the total distance that the object travels. Now, notice that the object started and ended at the same position. So your delta x, or your displacement, would be 0. So if you tried to go right in and do delta x equals 1/2 at squared plus vit, you're going to get an answer that doesn't make sense. It's going to give you an answer of 0. So if we want to know, okay, well, what path did this truly travel, we can actually focus on the max height. Because this is just that parabola, right? It's very symmetrical. Whatever you did on the way up is what you did on the way down. So if we can figure out the distance, or the final position of maximum height, all we would need to do is multiply by 2. So for a problem like this, you're going to focus on maximum height because it allows you to actually solve for distance rather than displacement. So we say that the initial position is 0. We want to solve for the final position. We're given the initial velocity. We can say, hey, I know that I'm focusing on the maximum height, so that's going to be 0, and then we have our negative 9.8 for acceleration, and we can solve for time. And this is kind of our first step. If you forget that final velocity is 0 at maximum height, then you really can't do the problem. So make sure that you're remembering that, and then the problem becomes pretty easy. We can solve for time. Using that time, we can plug back in and solve for the final position of that maximum height. And then we say, okay, well, it took 5.1 meters to go up. It's going to have to take 5.1 meters to come back down. So it's going to be a total of 10.2 meters. And you should get pretty used to problems like this. Problems where you start and end at the same position, really focusing on the fact that that's going to be symmetrical. And like I said, moving forward, we're going to do a lot of problems like this. So really hone in on this one. And if you have any questions, please see me. All right, have a good day.